Hello. So in this video I will be talking about solve multiple ways, which is a category of videos where I show you multiple ways of solving a problem and multiple ways of proving what has been asked of you to prove. Now, as I've said before, if you try and solve a problem in multiple ways, not only do you learn a lot more mathematics than, say, without experimentation, but after enough practice you will also start realizing that there exist long paths and short paths of solving some questions. And this, of course, comes in handy during your exams. You will look at a question and you will immediately know of the multiple paths you can take and which path is going to be the shortest for you. So that is really advantageous. But again, to find these paths, you first need to experiment and try solving a question multiple ways by yourself. Okay? So today I will go over this question from the Trigonometry Supplementary exercise of class 11th Mathematics NCERT. A pretty long statement to say in each video. Now this question is actually a very perfect example of where multiple ways of solving comes in really handy. So I will show you the short strategy and I'll also show you the long strategy. Right, I only know two techniques. If you have some more, you can always write them down in the comment section. So let us start. Again, as I mentioned before, in such questions, what I like to do is I like to rearrange the constants on one side, rearrange the lengths on one side. Okay, so I have a here and I have b minus c on the right hand side. So I'll take b minus c to the left, which gives me a upon b minus c, and I will evaluate a upon b minus c, and hopefully that will give me my answer. So let me write that down, a upon b minus c. Okay, now using the sine law, I have a upon sine a is some constant, so I can write a equals k sine a. I can write b equals k sine b and c equals k sine of angle c. Okay, now I can substitute all three of these back in this expression that I wrote. So I get k sine a upon k sine b minus k sine c. Okay, now the k is common in the denominator. I can take that out and it will automatically cancel out with the k present in the numerator. Okay, so let me just cancel it straight away. I get sine a upon sine b minus sine c. Okay, using the sine x minus sine y identity, I get 2 cos b plus c by 2 sine b minus c by 2. Okay, that is just how the identity works. And the sine a itself can be written as 2 sine a by 2 cos a by 2. Okay, remember we did something similar in the previous question, in the question number 9. So let me write that down. I get 2 sine a by 2 cos a by 2 upon 2 cos b plus c by 2 sine of b minus c by 2. Okay, now as we discussed in the last video, a plus b plus c, these are the angles of the triangle, equals pi radians, right? This is just a property of triangles. The sum of all the interior angles equals 180 degrees or pi radians. So if I divide this by 2 on both sides, I get a plus b plus c by 2 equals pi by 2, and I can split this line here, which gives me a by 2 and b plus c by 2. Okay, that's how fractions work. So I get b plus c by 2 equals pi by 2 equals pi by 2 minus a by 2. Okay, now I can substitute this b plus c by 2 here, which gives me cos of pi by 2 minus a by 2, which is going to equal, what is cos of pi by 2 minus x? That is sine x, right? So that gives me sine of a by 2. So this term, cos of b plus c by 2, is sine a by 2. So this sine a by 2 will cancel out with this sine a by 2. Okay, let me write that down. Wrong pen. 2 sine a by 2 cos a by 2, 2 sine a by 2 sine of b minus c upon 2. Okay, so sine a by 2 will cancel out with the other sine a by 2 in the denominator. I will end up with 2 cos a by 2 and 2 sine of b minus c by 2. Now I am not cancelling these 2's because of another reason, and I'll show you why. Okay, but let us keep a track here. We have cos of a by 2 in the numerator, and the question asks us to have cos square a by 2. Okay, so I still need another cos of a by 2 in the numerator for me to obtain this expression. Okay, so let us go ahead. How can I obtain another cos of a by 2 in the numerator? Well, one thing I can do is I can multiply divide by cos of a by 2 on in both the numerator and the denominator. Okay, so 2 cos of a by 2 upon 2 sine of b minus c by 2, again multiply dividing by cos a by 2, so this cos a by 2 gets multiplied with this cos a by 2, and it gives me 2 cos square a by 2. So we finally have what we want in the numerator. Okay, into 2 sine of b minus c by 2 into cos of a by 2. Okay, I have these terms. Now again, as I wrote here, that b plus c by 2 equals pi by 2 minus a by 2, along the same lines I can also write a by 2 equals pi by 2 minus b plus c by 2. Okay, so let us substitute that here. I get 2 cos square a by 2 in the numerator as we wanted, 2 sine b minus c by 2 cos of pi by 2 minus b plus c by 2. Okay, and what is cos of pi by 2 minus x? That is just sine x. Okay, so 2 cos square a by 2 upon 2 sine b minus c by 2 sine b plus c by 2. Okay, now this should be a little familiar to you. 2 sine a sine b, right? What is 2 sine a sine b? 2 sine a sine b Let me write that as x and y because a and b becomes a little confusing. What is 2 sine x sine y? What is minus 2 sine x sine y? That is cos of x plus y minus cos of x minus y, right? That is how the identity is. Okay, so I can write 2 sine x sine y as cos of x minus y minus cos of x plus y, right? I just sent this negative sign here and that flipped the signs of these cos over. Okay, I have 2 sine x sine y equals cos of x minus y minus cos of x plus y. So we can apply that here. Let us say that this is x and this is y. Okay, I get 2 sine b plus c by 2 sine b minus c by 2 as cos of x minus y cos of, this is x, this is y. I get b plus c by 2 minus b minus c by 2. Okay, minus cos of x plus y, x is b plus c by 2 plus b minus c by 2. Okay, now these fractions already have a common denominator, so I can go ahead and unify the denominator. I get cos of b plus c minus b minus c upon 2 minus cos of b plus c plus b minus c upon 2. Okay, now opening this bracket right here, if we remove this bracket, these brackets, the positive b becomes the negative b and the negative c becomes a positive c. Okay, the plus b, the positive b cancels out with the negative b. Okay, and on this side the positive c cancels out with the negative c. Okay, this gives me cos of c plus c is 2c by 2 minus cos of b plus b is 2b by 2. The 2's cancel out, so this gives me cos of c minus cos of b. Okay, so this term in the numerator, 2 sine b plus c by 2 sine b minus c by 2, ultimately equals cos c minus cos b. Okay, so I can come back to the main stream here and I can write this entire term as cos of c minus cos of b. Make sure you get the b and c's right. Cos c minus cos b. Okay, now what did we have on the left hand side? We had some constants, right? I just lost track of them. We had a upon b minus c. Okay, this equals a upon b minus c. Okay, now we can do some rearranging. The cos c and cos b can come to the left hand side and towards the numerator, and the b minus c can come to the right hand side in the numerator. So I will end up with something like a into cos of c minus cos b equals 2 into b minus c cos square a by 2. Okay, and that is exactly what we had to prove, right? So let me write that down. Hence proved. Okay, this is my short way of solving this question, even though it doesn't seem like it's short. If you do it by yourself, uh, you will be eventually able to solve this question in a few steps. That's all. Now let us talk about strategy 2, which is the long strategy, STR2, which is again to solve the LHS. Okay, so on the LHS for this question I have A into cos C minus cos B. Okay, now what I can do, whenever I have some cos involved, I can use the cosine law. Okay, I'm going to write just one of them down. As per the cosine law, I have cos of C equals A square plus B square minus C square upon 2AB. Okay, so I can substitute this entire thing here, and I can do the same thing for cos B. So let us do that. Cos C is A square plus B square minus C square upon 2AB, and cos B is A square plus C square minus B square upon 2AC. Okay, now you can see that we have A common in the denominators, so I can take that out common, and the A's will eventually cancel out. So let me just cancel them beforehand. Now I have fractions here with their denominators as 2b and 2c respectively. If I want to do some addition and subtraction, I need to take their LCM, right? Their least common multiple. So this term has to be multiplied by c on the numerator and the denominator, so that their denominators become common and I can do some addition subtraction. Similarly, this term has to be multiplied with b in the numerator and the denominator, so that the denominators of both the terms become the same and I can do some addition subtraction. Okay, so let us do that. C plus b square c minus c cube upon 2bc minus a square b plus b square c minus b cube upon 2bc. So you can already see that this expression has become a little nasty. We have cubic terms involved now. The powers are going to the order 3 and there are so many terms involved. That is why I do not prefer this approach personally, but again, it's up to you. If you want to use it in the exam, it's not a wrong approach, just a little tedious. So the denominators are common. We can perform some addition. I get, let me make sure that equal to sign is present. I get a square c plus b square c minus c cube, and opening this bracket I get this positive a square b converts to negative a square b, this positive b square c converts to negative b square c, and the negative b cube converts to positive b cube. Okay, always be careful when opening the brackets whenever there are signs involved, upon 2bc. Okay, so does anything cancel out? Nope, nothing, but we can do some rearranging. I can combine the cubic terms. I can say b cube minus c cube becomes one term, Oh, by the way, I just realized that I had some mistake here. This is not supposed to be b square c, this is supposed to be bc square. Okay, otherwise these two terms will just cancel out, and that is not so good. So b cube minus c cube plus, let's say I have b square c minus bc square, okay, plus, let's say I have a square c minus a square b, okay, upon 2bc. Now I can take a b common, not only just b common but b and c common from both of these terms, and I can take a square common from these terms. So let us do that. I have b cube minus c cube plus bc taken common from b square c just leaves a b, and when taken common from bc just leaves a c, plus a square c minus b, okay, on 2bc. Now what is a cube minus b cube? A cube minus b cube equals a minus b, a square plus ab plus b square. Okay, that's an identity, so we can write that down. I have b cube minus c cube as b minus c, b square plus c square plus b into c plus b into c, b minus c, plus, let us, we have b minus c here, b minus c here, and this term is trying to be a little b minus c itself. If I can take a minus common from this, then it would also become b minus c, right? Let me show you what I mean. Minus a square b minus c. If I expand this term, I will end up with minus a square b plus a square c, right? So note that this positive sign reverse to a negative, but eventually everything remains the same. I just took a minus 1 outside of this expression, okay, and I have wrong pen, and I have 2bc in the denominator. So since this b plus c is common here, b plus c is here, and I have another b plus c here, b minus c here, I can take this outside, I can take these common, b minus c, that leaves me with b square plus c square plus bc, b square plus c square plus bc, plus this bc, and minus a square, okay, upon 2bc. Now these bc's will add up, so I get b minus c 2bc plus b square plus c square minus a square upon 2bc. That's an ugly line. Okay. Now we have a 2bc here. What I can do is I can open this bracket and bring this 2bc inside the bracket. Okay. So in case you are having a hard time keeping track of things here, let me show you what I mean by a simpler example. A plus b by 2 can be written as a by 2 plus b by 2. Okay, and if c is getting multiplied with this term, then I can write this whole thing as c into a by 2 plus b by 2. Okay, so that's exactly what I'm going to do here. I come to b minus c, and I'm gonna take this 2bc as one term and this whole thing as another term. Okay, so I get 2bc upon 2bc, which will eventually resolve itself to 1, plus b square plus c square minus a square upon 2bc. Okay, so these 2bc's cancel out, b minus c, I end up with 1 plus, and what you should note here is that this term b square plus c square minus a square, this is nothing but the expression for cos of a, right? As per the cosine law, cos of a equals exactly this. So once you have figured that out, you can substitute this term as cos a here, and now the question asked us for something along the lines of cos, let me use a different pen. The question asked us of something along the lines of cos square a by 2. Okay, square a by 2, but we just have a cos a here, so that gives me a hint that perhaps I can use the expansion of cos 2x to solve further, right? Let me show you what I mean. Cos of 2x equals 2 cos square x minus 1. Okay, so if 2x is a, I have cos of a as 2 cos square a by 2 minus 1. Okay, so let us substitute this here, and we'll end up with b minus c 1 plus 2 cos square a by 2 minus 1. The ones cancel out, so what I'm left with is 2b minus c cos square a by 2, right, which is exactly equal to the RHS, hence proved. Alright, so this was a tedious method of solving the same question. As you can see, we went over some cubic terms, some cubic identities here, some extensive solving of at least 8 to 9 steps, and but eventually we were able to prove that LHS equals RHS. Okay, so this is just a tedious and a more long method of solving the same question. If you ask me personally, I prefer this approach, where you just take the constants on one side and you start evaluating that, and then ultimately you rearrange the final expression that gives you your answer. Okay, so that's why I said this question is a perfect example of why solving multiple ways can be extremely helpful. Now you'll know beforehand that if I go ahead and solve for the constants, that's going to save me a lot of time and a lot of complexity, instead of just brute force solving the LHS. Okay, so if you like this video, you can show your appreciation by pressing the like button, and if you want to see more such content, you can also consider subscribing to my channel. I'll see you in the next video. Bye bye.